going to try to introduce you to the wonders of Ceph and enterprise storage, if you are not a storage person. How many here would consider themselves open source people? All right. How many of you would consider yourselves enterprise compute or storage people? Okay, we have a bunch of sysadmins. Perfect. Okie dokie. So, well, without further ado, our agenda is to give you as much information as needed to be able to do some damage around Ceph, and to walk you through a cluster live for as much time as we have here so that you can see hands-on how it works. Now, what is Ceph? So, Ceph is a large-scale distributed storage system. So if you think of the storage on your computer, the hard disk or solid-state drive, Ceph is more of the kind of storage array that you find in a company, something like the NetApp or EMC box, the storage appliances that you have there. Ceph typically is used when you have petabytes of storage. You don't use Ceph when you have 10 terabytes. I mean, there are some cases where you do. Notably in Kubernetes, you do, because Kubernetes doesn't use much storage. It tends to be stateless. But in most cases, Ceph makes sense when you consume a lot of storage, or when you need all of its functionality, as in the case of Kubernetes. It is an enterprise class storage technology, so it has a lot of functionality that consumer storage like laptop hard drives wouldn't have. I see what you meant, Greg. I didn't understand bouncing. We don't want that icon bouncing around all the time. It doesn't want to die. Okay. So, you have complex storage requirements and you have a lot of data. That's where this comes from. Now, traditionally, the storage market is dominated by a couple of vendors. EMC and NetApp historically have been the big guys. And it's dominated by appliance-styled storage solutions. So you buy the hardware as a rack with the storage in it. The software comes as part of the deal. It's not something that you buy separately. Now that gives us the first buzzword here, software-defined storage. Software-defined storage is something that's been happening in storage where vendors are unbundling hardware and software. So you buy the software from one vendor, but then you use hardware from typically your compute vendor of choice, your x86 vendor of choice, Dell, Supermicro, whoever. What is going on with the projector? Oh, that's okay. So the dynamics that software-defined storage bring are kind of the ones that you are used with in open source, just a lighter version. Typically, as a buyer, when you buy open source, you know that the vendor doesn't have the ability to dramatically raise prices on you like VMware. Or some other recent events, because they don't have exclusivity. If an open source vendor does that, well, you go to another open source vendor. The software-defined storage or software-defined networking scenarios, the hardware vendor doesn't have that kind of power, but they still own the software part. So there are scenarios where things could go sideways, but that is what is driving things. Giving you choice in hardware is part of it. Moving to off-the-shelf hardware is part of it, and the economics are part of it. Unified storage system is another buzzword that rings around Ceph, because typically enterprise storage systems provide only some types of storage. Storage comes in block, object, and file forms. Block being your hard drive when you're formatting it, if you want to think about it. Object being AWS S3 is the most common case for object storage out there. You put things, you retrieve things, they're stored in buckets, that kind of thing. File is traditional file system overlay. Ceph is a unified storage system in the sense that it provides all three, and it's designed to provide them with as leading use cases, as you can use these to the full extent of, you can use them in anger to solve your problems. In a lot of enterprise storage systems, the solution is one or two. Maybe it's something that's great at file, and it has some object tacked on the side. Or it's something that's great at block. It has some object there because it needs some object to run OpenStack, maybe, things like that. So Ceph is truly designed to be a unified storage system, so it stands out. Scalable in multiple ways, we'll see, but performance and capacity are the big things. So in theory, you could continue to add storage to Ceph architecture forever. In practice, obviously, there are implementation limitations. What we see in our customer base is about 100 petabytes for object store use cases, around 10 petabytes for file and block use cases. In the community, we see larger scenarios. Like I've seen a 30 petabyte for file and block. But those are the typical numbers for what we see in IBM or Red Hat customers. The other thing is performance. Traditionally, storage of the enterprise kind loses performance when you add more to it. Because you're running through against some bottleneck. So you use more storage, what is the bottleneck? You're running out of it, whatever that is. In distributed storage systems where things are spread across many dozens or hundreds of nodes, the opposite happens. The more nodes you add, typically the more performance you get. Either you get linear dynamics where it kind of stays the same, or because you're never running the storage cluster at 100% all the time, because it's underutilized, you get these scenarios where suddenly you have performance bursts, or you have to manage the expectation of customers because they expect you to be always so incredibly fast. A while ago, I was visiting the Free Software Foundation. They are running their own Ceph cluster there. They were telling me improbable numbers of how unbelievably fast it was. And so I looked at the cluster and I said, well, it's because your benchmark is so small and you have 12 nodes. Basically, your storage is all coming from the RAM of the nodes. You never touch the disk. Or maybe it even came from the caches in some cases. It was a very small benchmark. But that's the kind of dynamics that you get when you have scale out and the cluster is underutilized. We like to call Ceph the future of storage because we're a little bit full of it, but hopefully that is the case. Linux of storage, however, is a more useful metaphor. Linux is the compute open source layer of choice for basically half of the world. The other half runs Windows, sadly for them. Ceph aims to be the same thing for storage. The open source layer, software layer for any and all storage. Now, the reason why the metaphor is interesting is that if you think about Linux, maybe, I don't know, 2002, kernel 2.4, what would you do in production with that? File servers, web servers, certainly. Print servers were a thing back then. Databases were still off limits. Oracle hadn't jumped the gun yet. So there were many compute use cases, but most of them were on Solaris in the Unix world. For Ceph, it's a similar story. There are, if you look at the price list for EMC, there are at least 60 use cases for storage. Ceph probably will cover all of them at some point, but our aim today is to focus, at least commercially, on some and be very successful in those before we go to the next one. And so some things Ceph does really well. Some things are more ambitious future projects. And yeah, so that's the word of caution. Now, Ceph is fully open source, LGPL primarily. And it is not open source just in the sense of throw it over the wall open source. It actually has a community, and a very good one. So we're very proud of that. We try to spend as much time and effort as we can in grooming this because it's an asset for us commercially. It's an asset for the project in terms of all the contributions that come in. And it ensures the healthy continuation of the project. as I was mentioning before, Ceph runs on commodity hardware. So if your vendor of choice is Dell, IBM, Cisco, whoever, you get the hardware from them. You usually choose the same vendor that gives you your x86 servers. That's where you typically start from. And then you install Ceph on it, and you have another vendor that provides you the support for the software-defined storage layer, as I was explaining earlier. Now, use the wrong hardware. This is the trade-off. When you're buying integrated, they figure this out for you already. When you're buying disaggregated, you make sure that you have a reference architecture. That's probably the most valuable thing that the support vendor can give you, so that you buy the right hardware. Because if you buy the wrong hardware, the performance is going to suck. There is absolutely no way around that. You have to have the right hardware. Or, well, either you buy too poor hardware and the performance is not good enough and you hit the wall immediately, or you buy really good hardware, but remember the story here is scale out. You're going to continue to add. It's going to be a problem because it's too expensive. Oh, I cannot afford to add more. So you really want to work with the software side vendor, tell them, oh, I want Supermicro hardware. What is the reference architecture for that? And figure out what is the right hardware to buy. Obviously, we have our own solutions, but you get to choose. Like we say in open source, you have the right to choose your own destiny. And we discussed the fact that object, block, and file are already covered. So all the various freedoms of the FSF are covered. Freedom from vendor lock-in is probably not an FSF freedom, but it's very much near and dear to our, to our heart in Ceph. And as some of you will know, we have transferred the Ceph team, all 300 of us, from Red Hat to IBM last year. And as part of the transition, IBM has confirmed with a public statement that you can find as a press release that the team will continue to contribute to open source. We're not closing off things or forking off on a strange side. And the contribution model will continue to be upstream first. So things continue as before. Yes. I'm sorry? So, no, I cannot share that. So, well, there is an interesting story, but the answer is no. We have clients for Power. So if you want to consume Ceph storage from Power, you can. And there are some people who do primarily OpenStack. They have OpenStack compute planes on Power, they have their x86 storage with Ceph, and they consume the storage from Power. But Power tends to be a rather expensive compute platform, so it's not an obvious choice to build a relatively affordable storage solution. Yeah, there is an interesting story about that I can tell you off the record, but ask me later. Similar thing about S390. S390 has clients, and there is also the OpenShift storage product runs on S390 because the amounts of storage there are small, and so it makes sense to just encapsulate the entire OpenShift infrastructure in the mainframe if you're doing that. But otherwise, mainframe storage is atrociously expensive, so you wouldn't want to use it as a layer and then put an overlay on it. You just use mainframe storage at that point. Ceph has a very long and rich history that we're not going to go into, but the point that I usually like to make is that aside from all the many users and customers and engineers that work on this, there are also about 6.5 exabytes of use of Ceph. So that makes it, I don't know if it makes it the largest software-defined storage solution out there, but it certainly makes it the largest software-defined open source storage solution out there. So when we're just getting started. Actually, while I am on that point, what are people using Ceph for? So primarily, they're using it for three things today. The community, there is a lot of Cephfs. That tends not to be the focus of the enterprise vendors as much. So actually, I'm lying. There are 4 things. So in community, there is a lot of Cephfs, primarily in HPC and research space at universities. In both the community and the enterprise space, there is Ceph everywhere. There is OpenStack. OpenStack is sort of limited to the niche of telco, to the vertical market, I guess. Niche is not. Vertical market is the proper way to say it, of telco, is where OpenStack is dominant now, and there is pretty much 2/3 of the install base of storage for OpenStack is Ceph, whether it's community or enterprise. In community, the numbers are even higher, actually. Then Ceph is used as standalone on-premise S3. So you have S3 in AWS, or you have S3 on some other cloud, where probably it's backed by Ceph, in fact. Or you can have S3 in your data center. And for these kind of hybrid scenarios, Ceph is dominant. That's where the very large clusters come from. The 100 petabyte scenarios, the 30 petabyte scenarios tend to come from object stores. And the last thing is overlay storage for Kubernetes tends to be very popular there because Ceph is a very sophisticated and mature storage technology. It's a little bit of overkill for Kubernetes storage today, but as Kubernetes gains ground in different use cases, and it moves beyond being purely stateless, it makes sense to have a robust storage layer there. So right now, the amounts of storage that Kubernetes consumes are small, but there are very mature things like OpenShift Data Foundation that use Ceph as an overlay on OpenShift to provide storage to Kubernetes. So, as I said, Ceph is distributed. So instead of having one large rack, you have many, many nodes. The many, many nodes split resources, compute, RAM, storage, and so on. It turns out that building distributed systems is hard. That's why we all have jobs. But the other thing is that distributed systems like Kubernetes and OpenStack are a heck of a lot harder than Ceph. So system administrators who are familiar with Ceph, who are familiar with the compute plane like OpenStack or Kubernetes, they do this in their sleep. They go, oh, this is easy, I'll just do it. Storage administrators are in for a bit of a hurdle because it is not a monolithic thing. It is something that has its own dynamics. Since Ceph scales out by adding resources, so you add more nodes when you need more storage, when you need more capacity, or when something fails. The important constraints in terms of designing the architecture are that Ceph is a reliable system built of unreliable components. Or as community member Florian Haas likes to say, Ceph is an infinite hotel that continues being open while some rooms are being remodeled and some other rooms are on fire. So the system remains operational even through these incidents, and there are different levels of resiliency that you can seek depending on what you're using the cluster for. The core thing that you expect of every Ceph cluster is that services are going to be highly available, at least. In some cases, HA+1 for some vendors, but at least HA. So if one component fails, there is another one. And at the level of data resiliency, you're going to be able to tolerate two failures. So you could lose 2 drives, 2 hosts, 2 racks if you're looking at that scale. Because we have 3 copies of the data in play when we do replication, or the replication designed by your Azure coding scheme in the EC scenarios. Upgrades and other scenarios of operational maintenance like that are also carried out without interrupting service. And the Ceph team is very much on the side of keeping data safe over giving you more performance. So if there is a choice between safety and performance, Ceph team always falls on the data safety side. There is also something that you can get as sort of a battle story, which is a couple of times a year, you see some vendor that comes out and says, my product X is faster than Ceph, usually a startup. And the problem for this, or I don't take it as a problem, but the reason for this is that in enterprise storage, you cannot benchmark against another enterprise product because the license of the other enterprise product forbids you from doing so. You cannot get the snazziest appliance and say, I'm benchmarking against that, because the terms of sale of the appliance say no competitive benchmarking. So what is one to do when you do a startup on storage? Well, you benchmark against the open source dominant choice. So a couple of times a year, I get phone calls that say, oh my God, so-and-so says that they are faster than Ceph. And usually the phone call is fraught with nervousness, and I'm like, that's great. They just told all of their customers about Ceph. Because really, we're not in the business of being the faster for speed's sake. We're in the business of being fast enough for what you are doing with the storage. And we're always fast enough for what you are doing with the storage, and then the game is scale it out to many users or to whatever scale out dimension you have in terms of numbers. It's not about a single point benchmark. But yeah, it's kind of funny with how it plays out because of the proprietary licensing about benchmarking. That's a bit unexpected, but we get free marketing out of it, so hey. Yeah? I'm sorry, can you speak up louder? Oh, upgrade methodology. Right, so I need to show you a bit more of how the technology works, but in terms of just bullet note, the way it works is that we roll through the nodes and upgrade one node at a time. And while that node is being updated, it's out of the cluster, and the rest of the cluster is serving your clients. So Ceph is elastic in the sense that you can add or remove nodes. Adding is a much more common scenario, but there are cases where you want to shrink the size of the infrastructure. Like virtual infrastructure, you don't want to keep virtual machines with your virtual storage running for no reason, if that's the case in an overlay. But typically, the thing is adding storage capacity or carrying out upgrades, not just in the scenario that the gentleman was speaking about, software upgrades, but there are also hardware upgrades. You want to replace the hardware at the end of life of the hardware after 5 or 7 years. You're basically doing the same. You're taking one node out, replacing it with the new hardware, and so on. There is one more scenario, which is, so the majority of Ceph deployments are single clusters. Because, as we said before, Ceph is highly available and highly resilient, seems robust enough. Most users don't worry beyond that point. But then there are users that have typically compliance needs, regulatory needs, where they have to have a backup scenario for losing the entire facility. So what happens if I lose the New York data center? Well, I have the Austin data center. So those scenarios are usually spoken about as disaster recovery configurations in the industry. And they're expensive because essentially you have your infrastructure twice. You can do a few tricks to try to shrink the secondary site a little, but they never really work out. You're still paying 90% of the bill. So I think the most successful scenario is that you have the primary site, and then your DR site is basically your test facility. You have a really, really nice test facility as a result, which is not bad, but at least you're using it for something while no great disaster is happening. The customers who do this are under regulatory need to do it, so for them it's not a choice. Architecturally for Ceph, it's an interesting thing because we operate in one way within one cluster, And then we have another way of operating when we're replicating data between two clusters, where we're copying data synchronously so that we don't affect the performance of the clients of the primary cluster. The other thing that's interesting is that Ceph storage, as we'll see in a second, operates all in one mode within one cluster. We store everything in a layer called RADOS, whereas when we are doing replication asynchronously between clusters, our replication modalities are very much data mode dependent. And that makes sense because the needs replication needs across different clusters for, let's say, object are different than the ones for block. And so you want to fit what these customers are trying to do with these geographical replications. So we've touched on the fact that Ceph is unified and provides all the interfaces. The underlying layer that I was just mentioning is called RADOS, which is reliable. I think A stood for autonomous or autonomic at some point, but what it meant to say is that it's self-managing, that it takes care of things that may happen to the cluster so that the administrator doesn't have to. If you are a storage old hand, you may remember 20 years ago things like your Unix system with directory names that with AA, BB, spread the directories in different places so that they would go to different partitions and different storage arrays, different locations, or whatever it was that was backing your thing. Ceph frees you from that kind of thing, or really any modern storage does. But the way Ceph does it is that when data is out of place, it moves it around the cluster on its own. When data loses resiliency because one node fails, and so you don't have 3 copies of the data that was on that node anymore, you lost 1 copy, it starts making a 3rd copy on the remaining storage on its own. It doesn't wait for you to replace a drive or ask you for a drive, just uses the free capacity of the cluster. So you just make sure that your cluster has free capacity, that's all you need to do. And you also need to, as I was saying before about architectures, you need to design a cluster so that, I mean, if you make a cluster of 3 nodes and 1 node fails, suddenly you're looking for a 1/3 of the capacity. That's not a good scenario, right? So Ceph can be supported in configurations of 3 or 4 clusters, 3 or 4 nodes, but generally it looks better when you are building architectures of 7 nodes and up. 11 is a good number to start with, depending on whether you're looking at performance or cost dynamics. If you're looking at cost, and maybe it's an object store, you pack drives more tightly. If you're looking at performance, and probably it's a block store, you're tuning for getting enough performance for your block use cases. Anyway, so RADOS is the underlying layer. It's an object store and stores the data for all of these types of technology, whether it's image, file, or object, and we'll see how in a second. It provides the facilities for erasure coding. It provides the facilities for data replication. So if your system is set up with replica 3 copies, it does that. If it's set up with an erasure coded pool, it does that. You can have pools that are in different configurations so that you can optimize the economics. Maybe have a pool that's cheap and not very performant for a certain use case, and a pool that gives you the maximum performance, but it costs more to deliver hardware to. And you can serve both out of the same cluster, and you can reallocate capacity between the two. So Ceph is very nice in terms of not having wasted capacity to one silo or another. There is just a single storage silo. LibRados is the API that you use to program this. It's not a REST API, it's its own protocol, and it is what clients use. Very few users write LibRados applications. Some of them are true geeks, and they do. And it's very nice because they can extract the maximum performance of the cluster, and they can do very clever things, but it's kind of a science project. It's not what you see normal users do. Normal users go through the 3 interfaces at the top. RGW is the object store. It stands for RADOS Gateway, but Object Store Gateway is a better moniker for that. It provides the AWS S3 interface and the Swift interface when you are running this as OpenStack storage. RGW is run by about 70% of community users and about 50% of our supported customers. And the biggest clusters are all big RGW object stores. So the RGW team has to deal with fun things, like the customers pushing, oh, I want another 10 petabytes. So they are the ones that have to deal with the 100 petabyte clusters and the implementation tweaks that go with that. The architecture of Ceph is made so that it can scale indefinitely, but the implementation, you always find problems, right? So as the customer keeps pushing the limits, the RGW team has to keep up with that. Yeah, I think that's enough on RGW. RBD is the block storage interface. It tends to be the highest performing one. When a comparison makes sense, I mean, it's a little bit of apples and oranges. It is the dominant storage technology for OpenStack, Cinder, Glance, pretty much anything that consumes storage in OpenStack uses that, except Keystone that needs an object store and so goes to RGW. Because of Ceph's dominance in OpenStack, about 75% of our customers use RBD. Between OpenStack and Kubernetes, we have that all over the place. What else? I think we're going to leave the rest of the technical details. CephFS is the file interface, and it is probably the most complex of the three because it's kind of magical to do in a distributed system, a POSIX compliant file system, but we pulled it off. We actually have the lead for CephFS who will speak right after me here. So you will get to hear all of it straight from the horse's mouth. And since we didn't do introductions for a very long time, I was the product lead for Block. So I was affectionately known as the blockhead. Now, let's look at the Rados layer. I think we covered the reliable and highly available at length, so I'm not going into that again. It is, the fact that Rados is scalable is ultimately the reason why Ceph is scalable. I mean, Rados does all of the hard things. There are complicated things at higher levels too, to be sure, but the storage parts are all in here. Data placement, replication, rebalancing, repair, all of that comes from Rados. It is strongly consistent, and because it solves all the storage problems in one place, it simplifies the implementation of services on top of that, whether it's the 3 services that almost everybody uses, or the custom applications that some adventurous customers write directly against Rados. So Rados is built of different daemons. The Ceph system has more than a dozen daemons running on different nodes that do different things. But these 3 are sort of the superstars. OSD is the daemon that takes care of the object storage paths. So the job of the OSD is making the hard disk that it's publishing. Typically, it's a hard disk. It could be a partition, but typically it's a storage unit, a hard drive or a solid state, being exposed by one instance of the OSD daemon. It will retrieve and store data from there. It will work with other OSDs to replicate data, and to rebalance it. And this is the thing of which you have hundreds or thousands in a cluster. This is on every storage node there is one for every storage path. The monitor is the entity that controls the state of the cluster. So it makes a map of the cluster, what machines are operational, what IPs they live at, and so on. Using an algorithm called Paxos, it decides when to release updates to this map. And there are 3 of them in a typical cluster. In a medium-sized cluster, there are 5. Very large clusters have 7, but it's always an odd number because they need to vote because of that's how the Paxos algorithm works. Let's not go there. Essentially what you get out of the monitor is the cluster map. When a node fails, when a rack fails, the monitor is going to go, oh, update to the cluster map. This rack does not exist anymore. And then the OSDs get the update. They start recovering the data that is presumed to be lost by making additional copies. The clients get a new map, and they start writing data in different places or retrieving data from different places. The manager is a relatively new entry. I think it came in the last 6 years or so. And essentially what happened is that we had too much code in the monitor, and the monitor is mission critical. If the monitor goes down, your cluster is, you have to lose all of them. But if you don't have monitors, you cannot get to your storage. But the manager contains management functionality for the cluster, and so it's not as mission critical. If you lose the manager, you lose the control plane to do administrative operations. It would be annoying as an operator, but it wouldn't affect the clients consuming this. So by moving code out of the monitor into the manager, we made the system more robust because we touch the monitor a lot less. Functionality that changes more rapidly, like systems management type functionality, lives in the monitor. And if somebody fat fingers some code and crashes a monitor, well, no big deal. We can fix the bug without data problems. So historically, this is how storage works. You go through some gateway, ask where the data is, and you get the data. And then you have HA pairs or some failover scheme for when that gateway fails so that you have high availability. But this is instead how Ceph works. The application goes to the entire cluster everywhere all at once. And the magic of this is that it does without a gateway. So the client knows where the data is in the cluster by using, the map that is going to ask. These slides are showing how the lookup would work. If you need to go to a server and ask for lookup data, you have a choke point, which is that box with the 3 question marks. I always need to ask where the data is. So you have a big bottleneck. Same thing as having a gateway. So Ceph instead uses calculated placement, which is having the map of the cluster available. The application can calculate where the data is. And the map doesn't need to be retrieved for every operation. The map needs to be retrieved only if something untoward happens, like failure of the node or failure of parts of the network or things like that. So only those things will cause a map update. So the normal operation for the clients is just talk to every node by determining this is the data object that I want to write, or this is the data object that I want to retrieve. You run an algorithm on some properties of this data, and then you figure out where it is on the cluster with no intermediaries. In a sense, Ceph is more of a peer-to-peer system than a storage system, if you look at it. It's because the lookup system is a distributed hash table. So you calculate where the data is, and then you either write it there or retrieve it from there. As I said, when a node goes offline, then that generates an update to the map, and the OSDs and the clients get an update saying new map, adjust your behavior accordingly. So there are 3 copies of the data on the cluster. At most, by losing one OSD, you lost 1 copy. Only of the data that was on that OSD. There are, let's say, 20 OSDs in this slide, so you lost 1/20th of the data. You lost 1/20th of your replicas. You have still 2 copies of that data. So the adjusted map lets you retrieve that data from different locations, and you can adjust your writing strategy similarly by having the new map. That's really what's going on. It's a little bit more complicated than that. Greg will go a little bit deeper, but that's the core of it. Rados data objects, which are the chunks that get stored in the Rados cluster, contain data, but they also have some metadata attributes that they can carry with them, like version number and things like that. There is also the possibility of using Ceph as a key value store, which is what we call OMAP. And in that case, you have keys and values instead of just plain blobs of data. Objects live in pools. I think I hinted at this before, so that you can differentiate some of the Rados behaviors between different pools. Typically, a very common scenario here is choosing which type of replication. So you have a replica 3 pool. It's going to be high performance for block. It's going to be high cost. You have your data 3 times. Or you have another place where you have, I don't know, 8 plus 6 erasure coding. Maybe that's not great for compute, but it's perfect for object store, and it's going to make your object store cheaper. You can have the same. You can have both in the same cluster, and sort of get the best of both worlds. And that kind of choice lives at the pool level. I think I walked you through the algorithm up to the pool level, which is, in a sense, the hash table part. And now I'm going to hand it over to Greg to explain PGs. Yeah? There are 3 identical copies, so it doesn't matter which one. I think so, more or less randomly. I mean, it's what happens based on the algorithm. There are some things that we do to produce affinity, but they're not very sophisticated. And in most cases, within a single cluster, affinity for a specific copy in terms of read makes no difference. Affinity makes sense in cases where you have a stretch cluster, where parts of the cluster are in one location and parts are in another location. It's kind of a fairly advanced topic that we're not touching on here today. But in that scenario, you want to look at which copy you're going to read. One other thing that, while you're talking about replicas, that is interesting is Ceph doesn't use RAID, right? So most storage is already replicated at the hardware level. So when you tell someone that's not into storage, oh, you have 3 copies of the data, that sounds very expensive. You're using a lot of storage. Well, not really, because any enterprise storage array is using RAID, and so you have replication at the RAID level. Ceph doesn't use RAID. I mean, we use RAID controllers because we like that, battery-back controllers, but we don't use RAID replica between the drives. The replication is all at the OSD level, so the overhead factor is not as large as it may sound.
All right.
Oh, sorry. I'm sorry, you have 3 Ceph? You have 3 Ceph managers? You have 3 Ceph monitors,
Well,
or managers? Which?
managers.
Okay. So the manager is not in the data path, and neither is the monitor. But the manager, whether they go offline or not, is irrelevant to writing. The monitor is relevant because you need to have access to the maps of the cluster. If you lose one monitor, it's fine because you have the other 2, and so your clients still have copies of the map, they still get updates of the map, so everything works. Well, you still have one, so you're still okay, but you should really run to the data center to start fixing things. But yeah, in general, you can survive 2 failures in that case, just like you would in storage. No, it doesn't count. As much as I like Ceph, that doesn't count. It's the same story as RAID is not backup. I don't have that slide in this deck, but RAID is not backup, right? Doesn't matter how many copies you have. Yeah, so within Ceph there is that disaster recovery scenario that I told you. It is pretty heavy-handed and expensive, but it is in line, right? So you basically have your data pretty much all the time. For backup, there are plenty of tools that can back up from a Ceph cluster, and so you run your backups in a very normal way. So for offline, basically keep doing offline backups the way you've done them before. I think we can interface with most backup tools just fine. All right, I don't want to run away from any questions. Are we all done? All right, Greg?
We'll keep taking questions, so raise your hand if you get curious. Right, so as Federico's alluded to, we have this algorithm. The algorithm is called Crush, which we use to place data in Ceph. And when you have an application, the information you need that the application actually gives to, well, when I say application, I here mean something like CephFS or RBD or RGW. Anything that talks to libRBD or to librados provides two pieces of information. It provides the name of the object, and it says it lives in this pool. And then libRBD takes those maps, it's the map of the OSDs, and it runs the Crush algorithm, and it says, okay, so the object lives in this placement group here at the far end, and that placement group maps to these 3 OSDs. And those OSDs, like Crush spits those out in an order, and the first one in that list is the one we send the IO to. And, you know, that's just sort of the way the system works. And then all these placement groups are mapped, you know, as I said, to 3 OSDs. You might ask why we use placement groups instead of, because sort of the obvious options are actually, we could replicate to the disks and have device mirrors, or we could replicate each object just to its own set directly of OSDs. But that comes with some costs. If you replicate disks, then the disks need to be the same size. This would be like RAID 1. Like if you, and if you've ever, you know, run a RAID system and had a drive fail, and then you need to like put the new drive in and resilver it, and it's just like that one drive sits there and copies, you know, an entire drive out, and that storage wall can be really, really high. If you try and replicate the objects individually out to whatever set of OSDs you want, that's a thing you could do, but part of doing recovery when an OSD fails is that you need to make sure you have the new version, or like the newest updates, which means you need to go trace out all the OSDs that have hosted the object and make sure that you get the one that's newest. And that means that every single device participates in every single recovery, and you need to like do lots and lots of expensive calculations to go trace the history of who owned that object in the past. So we take a middle ground where we shard like the pool namespace, like when you put an object into a pool, we take a very straightforward hash of that name, and then we hash that name, and then we chunk that hash range up into, you know, 100 placement groups, or 1,000 placement groups, or 10,000 placement groups, whatever is appropriate for the cluster. And the OSDs track the history of those individual placement groups, and when an OSD fails, then, you know, maybe it had 20 placement groups, and so all the OSDs which also held one of those placement groups go, oh, I lost one of my peers, I lost one of my copies, who's the new person in charge? Tell them they're in charge, and let's get on with life and recover the way we need to. Sorry. Yeah. There's also differences in the way failure works, but honestly, I don't think this is that interesting right now. Okay. So, Ceph is very, very big on keeping data safe. You might think this is an obvious thing in a storage system. It turns out it is not. So we always want our data to be safe. If you say that you want 3 copies of something, we strive to keep 3 copies available. If we don't have 3 copies available, we tell you, hey, we are currently degraded, and you know, here's how much of your cluster is working on recovery to get back to 3 copies of your data. And there's sort of this keyword here because you can decide how many placement groups you want in a cluster within a range, and you know, the more placement groups you have, the more peers every single daemon has, because you know, if you have 20 placement groups and 3 copies, then you know, every OSD is peering with, what would that be? 40 other OSDs. So if one fails, then 40 other OSDs get involved in recovering from that failure, which in some ways is really good because it means that they each only need to recover, 5% of their capacity out to somebody else. And instead of all targeting one particular OSD or like one particular drive to take that recovery bandwidth, it's recovering about 5% of a capacity to 20 other nodes, which is nice. Or I guess, yeah. So placement groups are just kind of, you can't do every single object individually for technical reasons, and you don't want to do a drive, so we have this in-between thing. The other thing that's nice, less about placement groups but about Crush, is that Crush lets you describe the way your cluster is shaped. You can put in your racks, you can put in your switches, you can put in, hosts live in, or drives live inside of a host, and you describe that all in the Crush map, and you say, hey, I want, one copy in each of 3 different racks. Or if you have, dark fiber and have a cluster spread out geographically, you can say, I want 1 copy in each of 3 data centers. And then it, adheres to those when it's doing placement. This Crush algorithm is pseudo-random. Basically, if you take a bunch of different inputs and provide to the algorithm and look at the outputs, it looks similar to a random output, which is important because you don't want to put in 10 things that all start with the letter H and have them all mapped to the same drive. That would be very bad. It's similar to consistent hashing, but better. And the reason it's better is that if you're familiar with consistent hashing, if you have 5 nodes and you add a 6th node, then almost all the data moves to a new node, and you don't want to do that with storage because moving all of your data around off of a hard drive is expensive. So we have bounds where if you have 10 nodes and you add another node, then you're bounded at, I don't remember, something like 17% of the data will move. It's a bit less than half of the proportion of added storage space. The inputs to the Crush algorithm are the cluster topology. This is just the OSD map, basically, and the description of the pool. Pools, we've been talking about 3 copies, and that's the normal system, but you can have a 2-copy pool or a 6-copy pool. You can have erasure coding, which is very, very wide and involves 20 OSDs, and a PGID, and then the object name is actually not part of Crush. The object name just runs a simple hash and says it's this placement group, and then the output of the Crush algorithm is just this ordered list of IDs. And in a replicated pool, then the first one on the list is the primary. Hooray! They get all the I/O, and they manage coordination with replication for the other peers. Yes. This is just a logical construct, and honestly, we're spending too much time on it. Yeah. Yeah.
In general, you don't need to understand this to do stuff, but you need to know that PGs exist because you're going to be having enough PGs in the cluster, regardless of PGs and stuff like that. This is where you need the view of how it works behind the scenes, but as an operator, you're never touching this. Only the developer.
Yeah. Right, so that's one of them. You can have disks of different sizes in a Ceph cluster, and that has implications on the way it performs, but is totally kosher. And the other one is that when a drive fails, the Ceph OSDs autonomously will re-replicate data to get enough to get back up to 3 copies. We're going to talk about 3 copies because it's simpler, but it's all the same principles. Which means that they need to know, which means that I need to say, oh, I have this peer, they died, I need to make sure that all the data I have that is in common with that peer is now getting moved somewhere else or getting copied to a new location. And if it's just like, oh, so it could just be literally the exact same thing as them, which means I need to stream all that data out to somebody else who needs to receive it all. But that means that you're limited in a recovery scenario to 1 disk's worth of throughput for recovery. And that, that 1 disk is extremely busy, so any I/O to that disk from like actual users is like totally stopped. And the other reason is that if you have, a 4 terabyte disk and the average object is 1 megabyte, you've got, I don't know, what is that, like 1 million objects on the disk? And if I have to go through and say for each of 1 million objects, what's the history of this object over the last, 30 days, because I need to make sure that I'm actually the newest version and we're picking up the newest version. Like, that's a lot of calculation. It's a lot of disk I/O just to find out who's supposed to be in charge of a thing and who has the right copies. So what we do is these placement groups, there's between 10 and 100 of them per OSD usually, and that's a manageable amount of tracking metadata. And it's a manageable amount of impact to the cluster's I/O needs when it's in a recovery state. And, you're not always in a recovery state, but if you talk about those 30 and 100 petabyte clusters, there's always a recovery happening. Users of Ceph, FS, and RVD and RTW have no idea about placement groups. Librados clients do not know about placement groups, but obviously Librados does. And if you're an advanced enough user, you can do queries to do interesting things. But yeah, there's no need to. There's no expectation that they do. It's not part of the sort of the standard contract. But yeah, if you're very advanced, you might care for. I don't know, does anyone here do like super advanced Hadoop administration? Yeah, okay, you don't care then. All right, so Rados supports both replication and erasure coding for data durability. We want the data to be extremely durable. That's, sort of the whole reason we exist is we make data durable at data center scale. The earliest implementation, because it was definitely the easiest, is replication. You write something to Ceph, then it goes to what we call the primary OSD, just the first one in that list, and the primary OSD writes it down to its disk, and in parallel, it sends it over the network to probably two other OSDs who write it down to their disks. That means, 3x replication, you only get a third of your total space as effective usable capacity, so it costs that much. But recovery is incredibly fast. You need 1 surviving copy, and you can just read it off of there and write it down somewhere else. It is not the same as RAID 1, but in a lot of ways it is. It's, if you lose two OSDs out of the cluster, you just read it from somewhere. But some people want storage to, to have less of an inflation overhead on how much storage raw storage they need to buy for a given capacity. So we also have erasure coding. Erasure coding is math. I understood it once 15 years ago. But the important part is that you do matrix transformations on a piece of data, and you can set up an arbitrary number of actual pieces of the data and then basically parity chunks. It can get more complicated than that, but we'll stick with that. Reed-Solomon encoding. And so, yeah, basically you say like, hey, I want to take 8 chunks and then be able to support 6 failures. So that's an 8 plus 6 code, and so you have 14 pieces of data. and you need any 8 of them to recover, or to be able to read the I.O., so your overhead is 14 over 8, about, oh yeah, it's 1.75 in that case. This is, this has impacts on the number of disk I.O.s you need to perform to serve any given end I.O., but it's really good for object storage with large, speaking S3 with very large objects. It's good because, if you're just doing a lot of streaming reads most of the time, or streaming writes anyway, then this is a good way to do it. It makes it cost way less, and you usually have a better ratio of IOPS to drive, or to capacity in that case. And I'm about to change slides, so I'm really hoping that this comes back. Okay, so pools are logical namespaces within a cluster. It is very common to have a Ceph data pool, and a Ceph metadata pool, and an RGW buckets pool, and an RGW data pool, and an RGW metadata pool. Pools frequently share devices, and so you can set different crush rules that say, where data should be stored, and then you pick one of those rules for a given pool. You can also say, hey, I have my SSD drives and my hard drives, and the metadata pools go on the SSDs and the data pools go on the hard drives. But it's perfectly fine for them to share OSDs and to share physical storage. That's totally fine. Let's see. As you use up your cluster, you will have less and less free space available. And the way that you expand your cluster is you say, hey, I buy a new storage node that looks like my other storage nodes, or maybe it's, the next generation and has a little more capacity, and I plug it in, and I run the software commands to add it to my Ceph cluster, and then the OSDs say, hey, my map has changed. There's this new thing that is supposed to be replicating some of my data. Let me replicate some of my data there instead. This is an online operation. It uses some of the raw disk I.O. capacity, but it is otherwise totally transparent to any users of the software or the system. It's really great. Within a given Rados cluster, it is perfectly plausible to have hard drive pools and SSD pools and erasure-coded hard drive pools, or even erasure-coded SSD pools, though usually you don't do that because they're sort of at cross purposes. But in the end, you have this reliable autonomic distributed object store. You took a bunch of, perfectly normal hardware, and you ran software on top, and now you just have this giant pool of storage. And your application says, hey, I want to use it, as an object, for Rados, it says, I want to be able to read and write objects in this pool. But then, on top of that, we build a file system, a block device, and an S3 compatible object store. So, RGW is itself an object store, so it makes sense to put it on top of an object store. This system speaks, it's S3 and Swift. These are HTTP interfaces, or RESTful APIs. And the Rados gateway is another one of the daemons. You run it either co-locate, depending on your system architecture desires. You can run it co-located with a monitor or with an OSD, or you can run it on its own servers. You will likely stick a load balancer, HA proxy, or something else in front of it so that you only have one point for your end users to talk to. And it speaks S3 out the front end, and there are a huge number of S3 clients. Out the back end, it speaks librados. And the gateway is responsible for sort of that translation. There are a few differences between S3 and librados. First of all, Rados likes relatively small objects on the scale of 4 megabytes. It's not a fixed size, but sort of that sort of thing. An S3 object can be, I think, a maximum of 5 gigabytes, and often is. So RGW has to chunk up those very large S3 objects into smaller Rados objects out the back end. Also, since Rados is calculated placement, there is no central system that knows what all of the objects in a Rados pool are. If you want to list the objects in a Rados pool, what you do is you go to every single PG and you say, hey, tell me what your objects are. And usually it'll give you back 1,000 at a time. And then you'll say, give me the next 1,000 objects starting at the letter B. This is expensive. It takes a while. It's not an operation you should run. S3 lets you list the contents of a bucket. And you do this all the time, and it is very important that it be fast. So Rados Gateway handles that, and it uses the OMAP interface on objects that Federico mentioned earlier to store those, and as they grow larger, because there is a limit on how much data you want in any given object in their OMAP, then it will then it does the work to split up that bucket index into a larger number of Rados objects and make that be transparent and scalable, and on and on. Oh, I should have advanced slides earlier. Frequently, the bucket index pool and the user info pool and the data pool are going to be separate pools. You can point them in the same place, I think, but you want your bucket index pool to be very fast. If you're doing a write, you need to go do hey, I'm going to write this object in the index pool, and then start the write off to the actual data, and then you need to there's some transaction processing happening in that index pool. So usually in an RGW cluster, you'll have some number of SSDs that provide the bucket index pool, and then the object storage might also happen on SSDs, but frequently is just very large hard drives because you're doing very large streaming reads and writes. RGW also has some very sophisticated functionality for replicating across different Ceph clusters. The Ceph project itself, or Ceph at its core, is sort of designed for a data center. You can run it, stretched across dark fiber, but it expects LAN sorts of latencies. Because we are doing replication 3 times, and we are very concerned about consistency, when you do a write to a Ceph cluster, and there can be caching in front in some interfaces, but when you do an actual write to a Rados cluster, then your write latency is going to be the time to send the message to the OSD, the time for the OSD to send its message to 2 other peers, the time for them to all write their data to disk and then to send it back to you. So if you have 10 milliseconds tacked on between the client and the primary and each of its replicas, that adds up fast. That can be an unpleasant experience. So, think LAN speeds for Ceph, but when you start deploying big object stores, people are like, hey, I can replicate my Amazon S3 to a different region on the other side of the world, and it happens for me. Why can't I do that with my Ceph S3 object store? And the answer is you can. But it uses a different mechanism than Rados. This happens within the RGW daemon cluster itself. So you can create zones of RGWs, and an RGW zone consists of a set of daemons and the pools that they talk to. And then you can do asynchronous replication of the contents of an RGW across different zones. And usually, you would expect those zones will be in different clusters that are geographically dispersed. But they don't actually have to be. You probably don't care, but it's good for developers. It's good for people who are, writing software that needs to do this later on, but are still in prototyping. And you can get a global view of users and buckets across all the zones. But a particular zone is going to be sort of the primary for a bucket, and it'll get all the data first, and then it replicates the contents of that bucket in that zone out to the other zones that are targets for that replication. But this is great for, having S3 compatible object storage that gets spread out all over the world. Let's see, what else about RGW? This is the part of the system I'm least familiar with. Yeah. So a bucket or a particular zone is responsible for a bucket, but you can have buckets on both sides getting replicated to the other. Am I saying that right? Oh, good. Yeah. So they can be active sites. It's just that if you try and do a write to the exact same thing on both sides, then there's then I think it redirects it. There's deconflicting, but deconflicting is always hard to do well. So we. But it'll be like, one side wins. It's not like like, yeah. Okay. So RGW has incredibly strong S3 API compatibility. The last time I looked, and as far as I know, it's definitely it's the most S3 compliant object store in the world outside of S3. We've had people who were very strong competitors come to us and say, "Hey, we noticed that you don't have a test in your test suite for this new feature, so we added one." And we're like, "Oh, clearly people like our test suite because they're using it for their own systems." There's security features of the sort that you would expect. You can do encryption and compression. These are features of S3, but I think we also pile our own on top for some specific use cases. It supports static website hosting in the S3 way. One thing S3 doesn't do is we integrate with Elasticsearch to do certain kinds of metadata searching. And you can get event streams out of it to do processing on your data stream or on the newly uploaded objects and things. But it's pretty cool. It is a thoroughly battle-tested solution. Yeah. No. The other thing I can tell you is that, like, almost everything that goes in via an S3 interface is going to be encrypted, and encrypted data is basically uncompressible. And obviously you can't dedupe it. So, like, dedupe is a feature in boxes. It's not a feature in, like, scale systems. And someone in the back, yes. Okay, so the question is if we have different networks for different purposes in Ceph. And the answer is that you can configure a public and private network in Ceph, and the public one is what clients talk to each other over and to monitors, and the replication is what OSDs do replication on. So at the software layer, those exist, but you're buying the hardware and the networking, so you can configure it behind that however you want. Those could be the same network. It could be that you have four Ethernet cables that you've bonded together. You can do whatever you can do with a Linux networking stack underneath Ceph.
Most customers have a private network that is basically just storage, which would be conceptually the same as frequently organized inside storage blocks. So that tends to run in clear, unencrypted, segregated, physically segregated. And then they can have client-facing network that's serving the data, which is usually
Yep.
And one further consideration that's useful there to share there is, so there was work for other storage, for other networking technologies, but essentially all of Ceph is always 10 gig or 25 gig per. It's not, we don't really use other fibers. I'm sorry, other networking layers. And that is part of the tendency to use common off-the-shelf parts rather than dedicated
Oh, and another one.
So,
Sorry, do you mean IP4 and 6, or? Yes.
in the project, it is, well, it's community, it's supported and in terms of vendor, we as a vendor support dual stack in the sense that we can have either or. We don't like to have them both at the same time. Although technically we could talk about that. I think that the Open Data Foundation may be planning to test this. I would have to do stuff.
Yeah. Anyway, open source version totally supports this. You can do it.
My community project has said that this is fine a long time.
Yeah. Yep. I'm sorry, can you speak up? That's fine. Yeah. So Ceph consumes Linux block devices. And if it looks like a Linux block device, Ceph will consume it happily and do the right things. Federico mentioned we like RAID cards, and that's true for some use applications because RAID cards, if you configure them correctly, we still use them in a JBOD array, but you can do faster commits because RAID cards, enterprise RAID cards have caches that are battery backed. So it's just about disk I/O latencies. And if you have, drives that have battery backed caches, then the RAID card doesn't add anything better than that. Okay, so that's the RTW gate, the Rados gateway that speaks S3. Now let's talk about block storage. This was actually the first stable offering of the Ceph project because it turns out that block devices, when you have a reliable autonomic distributed object store, are pretty simple to layer on top, at least for basic features. We've spent, a lot of time adding more complicated and interesting features, but just having a block device is pretty straightforward. So RBD support is a user space library, librd, and also in the upstream Linux kernel for 14 years now. So you can just take a bog standard Linux kernel and mount an RBD image on it. And when you create an RBD object or an RBD image, it's a CLI tool or available through a GUI website that the manager hosts or whatever. You specify a size for it, and it creates a little tiny index header object that specifies what the block device looks like and what its sort of object naming scheme is. And then if you want, and then it just chunks up a block device into lots of little objects, usually of size 4 megabytes. So if you write it index 0, then you'll get the first object, and if you write it index 1 gigabyte, you'll get the 256th object in that RBD image. But it's a thin wrapper around Rados to do that translation mapping from individual objects up into a block device address space. The storage is, out in the Rados cluster. So this is a great fit for anything you're running in virtual machines where you want to be able to migrate them around arbitrarily, which is why OpenStack loves Ceph. We are like this is the perfect storage system for OpenStack or for, any kind of private cloud like that. And it is integrated with everything. I am sure there's an open source project out there that provides storage that is not integrated with RBD, but I have no idea what it is. RBD built a lot of more interesting features besides just a block device. You can take snapshots of an RBD volume, and they are instantaneous. Rados provides a per-object snapshot functionality, and librrbd is, again, a thin wrapper around that. Snapshots are read-only instances that are copy on write, and belong to a particular image with point-in-time consistency. You can also create clones of an RBD volume. You can install a new Ubuntu OS on a 100 gigabyte RBD volume and take a snapshot of it, and then whenever you have a customer come along and say, I want a new Ubuntu volume or VM, then you take a clone, which is pretty much instantaneous because all you're doing is tweaking those RBD header objects of the snapshot of the golden image. It's a writable overlay, so if the new object in the clone exists, then it reads that one, otherwise it falls back and reads the snapshot of the underlying image. And those clones can themselves be snapshotted and resized and renamed and cloned again, yada, yada, yada. This is all, as I said, pretty much instantaneous, constant creation time. It's all copy on write, so only change data uses any space whatsoever, and it works great. Oh yeah, okay, so we got a picture of the data layout here. So on top, you got your virtual block device, you got the little header which says here's the name, here's how big it is. We've been talking about chunking data up into 4 megabyte blocks. You can do more complicated things, but rarely care to, but that's the striping. When you take a snapshot, you give it a name. The header says, here's all the snapshots and what their names are, different options. And this is where we coordinate if you want to do exclusive locking on an RBD volume, which you can do. You might care about that for failover scenarios in your cloud computing environment or whatever. The locking happens at the header. And then the data objects are, again, just little 4 megabyte objects that map to a 4 megabyte space of the address range. The objects only exist once they're written to. The space within an object is only consumed once that space within the object is written to. And usually RBD volume or RBD pools are replicated, but you can erasure code them as well with the subsequent change in the performance characteristics. RBD also supports yes. The default for everything in Ceph is 4 megabytes. You can configure that at the various layers if within certain bounds that go up to, depending on the layer, 100 megs or a gigabyte. But there's not a great reason to change it unless you know a lot about the system and your workload. Yep. Okay, so RBD supports asynchronous replication in two modes. One of them is you can do data journaling. In this mode, when you do a write to the volume, it writes to the end of a journal. I am writing these 4 kilobytes to this block offset, and then it also goes off and writes that into the actual normal RBD image. And then that journal is consumed by an RBD mirror daemon, and it reads that journal, and then it writes it out as a Rados client to a different Ceph cluster. So, it is behind in some fashion, and if the cluster A dies while the mirror daemon hasn't fully replicated the entire journal out into cluster B, you will be behind by some amount of time, but you will have exactly an exact crash coherent copy of what the image looked like at some point in the past. And you can bound that with your networking and your I/O capacity and everything else. The RBD mirror daemon is scale out in HA, but also, yes, this is ludicrously expensive because you're doing a full data journal of everything you write and then reading it out and writing it out across the network. So if you have, rapidly changing systems, maybe this is not the right solution for you. So you can also, did you make a new slide for this? Hey, you did. You can also take snapshots of the RBD volume in an interval, and the RBD mirror daemon can consume those snapshots and write them out to the other cluster asynchronously. And Rados has interfaces for, it'll have to go query every object, but Rados has interfaces for querying what are the snapshots on this object, what's the byte ranges in which those snapshots differ. So it goes off and it does efficient reads to only transmit the change data in that 30-second or 5-minute or hour-long interval. RBD has other nice features besides integrating with every storage-consuming open source system on the planet and mirroring. We've got an RBD top tool that shows you the I/O activity happening within RBD in a Ceph cluster. You can set quotas on users and volumes and yada yada. You can specify that RBD volumes live inside of a Rados namespace and restrict users of RBD to particular namespaces so that, you can give direct access to VMs or Linux hosts that you don't control completely, but that you sort of trust, and prevent them from from accessing or trampling on other people's data. You can import and export these images to both RBD formats and like QEMU or no, not QEMU. Well, yeah. Anyway, whatever the block device compressed format is, which QCOW. Thank you. You can import into from QCOW2 to this. You can do incremental diff between snapshots and shift them off to some other backup solution of your choice instead of using RBD mirror. And there's a little trash feature because it turns out that even in systems like this, sometimes people delete things they don't mean to. And, all right. As I said before, there's Linux kernel client. We also have an iSCSI gateway. There's a coming out imminently. You can go look at the pull requests, NVMe over Fabric gateway. It's integrated into the NBD block device in Linux. And then, librd, the user space implementation of this, can be linked directly into your library. This is how KVM works with it. And various other things. And now we get to Ceph. This is my project. I mean, I've worked on most of these, but this is mine. This is my baby. And Ceph is actually the reason that Ceph exists. Ceph was created initially as a PhD project after Lustre started getting rolled out at national labs to fix all the problems with Lustre. And it turns out that a file system is way harder to write than a block device is. But it is stable now, and there are customers from lots of companies who use it. There are customers of many companies using Ceph. So, Ceph is a distributed network file system. It looks, once you mount it in a POSIX environment, like a perfectly ordinary POSIX file system. It follows the POSIX semantics. It does real file system things. It is not dressed up the way like HDFS is, or the file system that makes your S3 bucket look sort of like a file system, as long as you don't do anything too weird, like try and overwrite part of a file. So it supports files and directories inside of a tree, and you can hard link them to each other, and you can do renames, and it all works. And if you have 3 clients reading and writing to the same file, then you get coherent answers out that reflect the real POSIX requirements of doing that. So it is fully coherent and cache consistent. If I do a write from client A, and then a client B does a read, it sees that data like as soon as the read will serve that actual just written data from the other node, whether you've done communication between those nodes on your side or not. And Ceph is really cool because it runs on top of Rados. All of the data in the Ceph file system is stored inside of Rados, whether it's the file data or the metadata that belongs to the file, or the metadata that a file system needs to keep track of all of the files in the system. So the ability to do fast writes of existing files is controlled by the characteristics of your Rados cluster. If you want it to be faster in terms of throughput, you just add more Rados nodes, and your file system is now faster. Hooray! And if excuse me. Can you grab the water for me? Thanks. The number of files it scales with the number of metadata servers. And this is actually not the number of files in the file system, but the number of files which are actually in use by a client. If you can have 1 trillion files in this file system, and if you only ever use 20 of them at a time, you can have a teeny tiny little MDS server, because all it ever needs to deal with is like 20 inodes plus the directories that lead to them. And so MDS servers are basically big memory caches of stuff that already lives in Rados, and that handle the coordination with the clients and the like, okay, there are 37 clients with this file open, and here's the permissions I've granted each of them to keep it possible for 37 clients to coherently access the same set of data all at the same time. So the question was about the performance impact. Like the performance impact of multiple clients, or? Okay. So, yeah. So, do we cache anything in the client itself? And the answer is, that depends on whether we can do so coherently. If there is one client to a file, it will get buffer and cache capabilities that allow it to read data and remember it, or to write data but buffer it before it sends it out to the OSDs because maybe it's going to be overwritten again. But once you have multiple clients accessing a file, obviously they cannot read each other's caches. And so at that point, we move into a synchronous mode where I/O goes directly to the OSD responsible for that range of a file. And to serve a read, you go and read it from the OSD. To serve a write, you write it to the OSD and then respond back once the write is complete. So it depends on, how it's being used. If all the clients are readers, then you can cache it all you want. It's great. Yeah, so the important thing there is that the MDS needs to be sized with the amount of metadata activity that's happening. So petabytes of data doesn't actually mean very much from the MDS metric, because if you have very large files, that could be like 10 gigabytes of metadata. But if, it's all 4 kilobyte files, then that's an insane metadata workload. So when you're sizing the MDS, you really think about the number of files that are in use at a given moment, not the total storage of the system. No. The Linux upstream kernel supports Ceph, and you can mount it there, but there's also a Fuse client, and there are backends for systems like NFS Ganesha that speak Ceph out their backend and present NFS out the front. Yeah. I mean, it doesn't have to. Like Linux supports it. Lots of. Okay. Yeah. So that's the benefit, is that when you have a Ceph system, the clients speak for metadata requests. If a client wants to create a file, it says to the MDS, hey, make a file for me and give me back the inode. I want to rename it or put it into a directory, do that for me. But when you do the file I/O to the data to the file, you just go out and speak to the OSD that hosts those objects that are backing that file directly. So if you're using Linux, then yes, there is a kernel. Like you need some interface that presents a file system, and that can be, yes, the Linux kernel client. You can also do a Fuse mount. If you can't modify your kernel but can run Fuse, you can do that. If you're building your own custom applications, you can link to libcepfs. Yeah, there's community Windows drivers that I think run. I don't know what Windows permissions you need for that. Actually, that's a little sloppier. Yeah. Yes. Yes, and it is very complicated because it depends on what you're doing. In general, the kernel client is going to be faster than the Fuse mount, but the user space, if you're using it directly from a process, is faster in some cases and slower in others. That they're different implementations, so they have different strengths and weaknesses. Okay. let's see. So I think I went through all these things already. I actually didn't talk about scale. Yeah, so I think we've run tests up to 128 MDS servers. It scales pretty well. A single MDS can only do, depending on the operation, between 10,000 and 30,000 operations, like file operations per second. But that doesn't mean that your cluster is limited to that capacity, because the MDS aggressively spreads out authority to clients. So if you do like a listing on a client 20 times, then you're going to do the listing once to the MDS and then satisfy it out of the local client cache the subsequent 19 times. Similarly, if you do a file create and then start changing the mode and obviously updating the timestamps and whatever else, like that's going to happen on the client, and then it'll just sort of flush those out to the MDS in the background. So it's pure memory operations most of the time, unless there's conflicting access. So I alluded to this before, but metadata for Ceph is stored in Rados. The client talks to the metadata pool. The metadata pool has objects in the Rados cluster for every directory. It has a journal of the updates it's performing, which are again objects inside of the Rados cluster, but are separate from the directories. There's a few other special objects for doing random things like tracking snapshots. But this has some really fun properties. Like if an MDS server dies, you turn on the MDS daemon somewhere, anywhere that can talk to your Rados cluster, and it comes up and it does and it replays the journal, and it gives the clients a time to reconnect so that it can reestablish coherent state with them that might have been lost. And when I say coherent state that might have been lost, I mean the permission that clients have to do things to files that may be timing out. Not like, file data or committed updates, or like anything that's been fsynced is definitely for sure safe. But you can just turn on the MDS server in a new location or in the same location or whatever, and it just goes off to the Rados cluster as a normal Rados client and reads that data back, and then life goes back to normal. And there's the monitors maintain a map of the MDS servers, and so the clients see, hey, there's this new MDS server that I should be talking to now because I guess my old one died. It also has this fun property. Okay, we don't have it here. That you can scale the number of metadata servers more or less arbitrarily. Logical metadata servers exist because of the journal. But if you say, hey, I have one MDS server and now I want 3, then you turn on 2 more MDSs and you tell the system to actually use them as actives instead of as hot or cold standbys. And then, depending on how you've configured the system, there's an MDS balancer that will try and balance the workload across all those servers, or you can do static or configurable pinning of your own preferences to split the workload out among them. And that all happens, like the system manages that. It happens more or less behind the scenes, and you don't have to worry about it too much. Ceph also supports snapshots. You can go to a directory, and you make dir inside of a special .snap namespace folder in that directory, and then if you go look at that newly created folder you created inside of the .snap dir, it is a snapshot of everything in that directory and the directories underneath it. And you can do this in arbitrary locations. These snapshots can be, you can snapshot, like the /home/Greg folder, and then you can later snapshot the /home folder, and then you can later snapshot the / like the root of the file system. And this all is totally fine. I will note there is one exception to that, which is that we will later talk about subvolumes, and subvolumes must be snapshotted at the root. But that's a special case to support mostly those specific requirements of the system. Yes?
You have a snapshot at the root, and say you have a subdirection that's got a lot of data in it. Are you able to keep the snapshot for every other direction, for the rest of the direction, wipe out the snapshot of it,
No. When you create a snapshot, it is a unit, and you create or delete that snapshot all at once.
they have to target where the snapshot
Yeah.
is defined,
Yeah.
everything except for that snapshot on them.
Yeah.
Can't
Yeah, you can't delete a portion of a snapshot, unfortunately. The way, unfortunately not. These snapshots are point-in-time consistent at a per-client level. So if you have 20 clients working directly, you snapshot it, and then you might get the data from one client being a little later than the other. That is about to change for Squid release, where we have the ability to quiesce I/O. Though those are, quiescing I/O means stopping it, so maybe you don't want to do that. Anyway, no one's actually complained about this to us over the last 10 or 15 years, but but we realized that we cared about it. It's, oh yeah, the snapshots are easy to use, as we talked about. It's just make-dir. I mean, there are other interfaces if you prefer them, but this one, when you mount the file system, you need a key to access the cluster, and that key specifies if you're allowed to create snapshots and in what folders or Rados pools or whatever you can do so. But as long as you have the permissions, you can just do it from the POSIX UI. And again, these are pretty efficient. Snapshots are built on top of the Rados individual object snapshotting layer, so they only consume space when changes are made after the snapshot is created. Snapshots are read-only. And in the MDS server, it does some metadata twiddling to create the snapshot, and then in the future, as you make changes, then it does a copy on write of the metadata as well as the file data inside of Rados. Yes. I'm sorry? Okay. So that's a good question. He asked if snapshots are counted under the same user space quota. And the answer is that Ceph does have quotas. Quotas are enforced entirely client-side and they're lazy quotas. They're not up to the millisecond accurate in terms of data used and whether you're against the quota. And snapshots and quotas do not interact in any meaningful sense, which is why you need permissions to create snapshots. But yes, snapshots do exist. They're good for an environment where you control the clients. If you don't control the clients, we recommend that you go through a Samba or an NFS or something gateway, because Ceph clients, as we said, everything's fully coherent. So if you have a malicious client that gets permissions to read a file, then it can prevent anyone from ever writing to that file again by just holding onto those permissions. It's super bad. Don't want to do that. We will eventually evict them, but it'll be like 5 minutes later. And unless you do something specific to deny access from that key, then they can just do it again. So you don't want that. But Ceph-VS, it consists of metadata servers talking to Rados pools. You can create multiple Ceph-VSs inside of a Rados cluster because you can give them their own pools and their own metadata servers. Well, it has X-adders because that's part of POSIX. It supports flock and functional file locking in the way that you would expect because that's part of POSIX. It has quotas because people asked us for them, and it satisfies many use cases, though not all of them. You can, and this is the way that Rook with Kubernetes and OpenShift tend to use it, and a lot of the OpenStack users via Manila. There's a subvolume library that creates folders inside of a special directory and generates access permissions for only those folders and makes sure those folders are isolated from each other that you can give out to end users inside of a semi-trusted environment, or that you can provide to your NFS Ganesha server to provide out to actually untrusted users, but while maintaining security as much as possible across the whole system. Yes, okay. So Ceph-VS also supports storing data in different pools. You can have, and you map that data at the directory level, and then everything underneath it inherits it until you provide a different policy. These policies are accessed and manipulated. There's other interfaces, but mostly by talking to virtual X-adders on the directory that you can say, hey, there's a data layout X-adder, and you can set the pool that data inside of that directory will be created inside of. That doesn't move data for you that already exists, but any newly created file inside of it will write to the place that you tell it to go to. So you can have bulk data that lives on hard drives and fast data that lives on NVMe devices, or some data that is replicated and some that is erasure coded or whatever, because you can just have an arbitrary number of Rados pools that are used to store file data. If you are in the HPC world, you may be interested in lazy I/O, which lets you turn off the coherent caching, and you manage it yourself. Let's see, what else do we have here? Oh yeah, okay. So, as we talked about earlier, Ceph has been in the Linux kernel since 2010 or 11 or something. You want a pretty up-to-date one though, because you want to support the newest features and you want to get all the newest bug fixes. There is a Ceph fuse binary that uses the file system and user space interface. We have NFS, and the Samba VFS has existed for a long time and is getting dramatically improved this year, like as we speak. And libcephfs is a library that you can link in. So we have in the past supported people using cephfs instead of HDFS inside of Hadoop or in various other places, and that way you can talk directly in your user space application out over the network to get fast access that doesn't require kernel updates or upgrades or anything. And that is an awful lot about most of the Ceph project, though there are a few things we haven't touched on. So Cephfs, this is actually, I don't know how long the dashboard's been around. It's been around for a while. It started out as a third-party thing on top of it and got integrated into the entire upstream project. So the dashboard is a website GUI that runs inside of the Ceph manager process and lets you manipulate your Ceph cluster and do management and day 2 operations and look at metrics and get alerts and all kinds of cool things. That's built on top of a lot of APIs and monitoring that exists in the CLI interface, and that you can plug in directly yourself via other mechanisms if you prefer. So we have warning states. If you lose an OSD, then we'll say, hey, this proportion of your data is degraded because it only has 2 copies, and you can watch it and get updates on that. There's integrated configuration management. You can say, I want all of my OSDs to get this new parameter, or all the OSDs inside of this rack, or this one particular OSD to get these parameter changes. You can read these things. Is any of it particularly that you want to particularly call out? Okay. I think. Yeah. I guess the one I will talk about is telemetry. It is 100% opt-in, but we have joined the horde of projects asking for telemetry on how the system is being used, because we're a distributed storage system, and we really want to know what interfaces people are using so that we can know if we should be devoting more effort to it, or what features they're, well, we don't do a lot of feature reporting, but at least what interfaces, and the big one is crash reports. If you turn on telemetry and a daemon inside of your cluster crashes, then a report will automatically get generated inside of our tracker. And we scrub those periodically and can correlate them and be like, oh, everyone's seeing this one, what's happening? As opposed to, that's your hard drive. Your hard drive's bad. Fix your hard drive. You have a number of installation options. The Ceph upstream generates and maintains Ceph ADM, which is an orchestration interface around containers and SSH. Rook is sort of a sister project of ours, which is the Kubernetes interface for installing and running and operating Ceph. There's also sort of one of the previous ones was Ceph Ansible, and that's still alive, though gets a lot less attention. There are Puppet, I don't remember what those are called. Are there recipes? It's been a while. Manifests? Yes, okay, so there's Puppet manifests. Canonical maintains microceph with Snap and some other stuff around it. DeepC comes from SUSE, okay, SUSE DeepC. And we do explain how to do your own installation, which used to be what we expected everyone who installed Ceph to do, but it turned out that was wrong. So now we have these other more opinionated installers. But you can definitely go still install it yourself. We have like 3 more ways of running Ceph that developers use. And the Ceph community. Ceph is open source. It's mostly LGPL version 2.1. There's some bits that are Apache licensed or whatever based off of the projects that we're integrating with or that we pulled from for things. You can go look at the upstream GitHub and Tracker's Redmine. This is all public. Like, we don't do anything. I mean, people have conversations in hallways sometimes, but like the pull requests are public. You can go look at them. You can go read them. We've had like 4 in our history that were private because they were security related and we had embargoes. You can see the community meetings and the stand-ups that the developers are pretty much all in at least one stand-up every day. We have mailing lists for developers and for users, and we're more on Slack now, but it's still bridged to our old IRC rooms if you prefer that access mechanism. We do releases, generally a major release every year, and then point releases for the last 2 or 3 major releases that on an ongoing basis for useful or important backports to fix bugs and everything else. We're distributed in a wide variety of distributions and other alternative installation mechanisms. Proxmox, we'll deploy Ceph for you. And we integrate with cloud ecosystems. OpenStack, like I said, loves us. We're basically the reference storage installation for everything that OpenStack does at this point. We're big in Kubernetes, though a lot less dominant there. We've been in KVM for ages. Obviously, we have clients inside of the Linux upstream. And Ceph has a foundation. Lives inside the Linux Foundation and owns we have a big upstream testing and CI infrastructure and, run the Cephlicon community conference event and Ceph days and things. And we have many people participating that way, in addition to just technical interactions. Sorry, I spoiled Cephlicon. We also have Ceph days. Those tend to be smaller and regional. Websites, check out if you're curious. Oh, we forgot to update this slide. Cephalon 2024 is happening. And here's more links. And I think that's what we got presentation-wise, and JC is going to come and actually show you Ceph. Any questions before that happens? Have any use cases in HPC specifically, and then I lost it after that. I heard you say luster, so I can't talk about the difference, but. Okay. Okay. Yeah. So, what are the challenges breaking into HPC? No. Technically, compared to Lustre, there are some pretty key differences. First of all, Lustre is definitely faster at file I/O than Ceph is. And partly that may always be true, but also there aren't enough people who are focused on that in the Ceph community, so that could get better. And that's file I/O. And I mean, because we do 3 replicas, we expect our data to be safe. If you work with Lustre, you have definitely lost a Lustre file system in your working career. And people have had Ceph crashes, but they have not lost a whole file system. And so that's just a sort of philosophical difference between them, but it does, change what you're going to be going for. So Ceph FS was initially conceived to solve the resiliency problem and to deal with metadata scaling. Lustre has, in the intervening 20 years, gotten a lot better at metadata scaling, and I can't really speak to the details of that because it's been a long time since I looked and I was never a Lustre expert. But they have gotten better at that. But also, CephFS is for, and there are some specific features that Lustre users really expect that have never been implemented in CephFS. And it's because there's never been enough momentum to make it happen. The big one is that CephFS, the coherent caching is all file-based, so we don't do the byte range access locking, and that's a key part of, not just Lustre provides it, but that's a key part of many HPC applications. And you can blame whatever the not quite Lustre Foundation was in 2012 for the fact that Ceph never implemented that. OpenSFS, that's it, because we asked them for money, and Oak Ridge told us we would get it, and then they turned us down. But we are faster for some kinds of work cases. I went to Oak Ridge once because they ran some experiments, and the HPC storage lead wanted to see how fast something was, so I ran a command and it was done, and they were like, oh, that was faster than we expected, so we ran up and put it in a loop to run 10,000 times, and I was like, that'll take a while. It hit enter, and then it was done, because it ran once and then was in the client and was entirely satisfied out of memory, which blew their minds, because Lustre doesn't work that way. But all that said, there are HPC users of CephFS. CERN is one of our biggest users, and that started in definitely not their HPC, but in their IT infrastructure. But every year it pushes a little closer and a little, it's never going to be the dump for their actual sensors. But they do run some of their aggregation on Ceph now, I'm pretty sure, their second or third tier. CERN, sorry, CERN, yeah, yeah. How many admins do you need? So, yeah, okay. Yeah, I mean, the thing is that people who are used to being storage box administrators find stuff hard to use, but people who are Linux administrators or OpenStack administrators or or HPC administrators are this is so easy. Because yeah. And that's because Ceph it's basically a set of, it's a set of Linux systems, and it works the way you expect Linux systems that are doing this to work, from an administrative perspective. I mean, I don't have any idea about the administrative overhead. Yeah, I mean, he does the IO 500 every few years. And I'm trying to think who actually does HPC workloads, because we do have people in the community, but we sort of see them at conferences and then they mostly don't talk to us. They're just yeah, it works. Yeah. The national labs we hear from a lot less now. I think there's still some at Sandia, though we haven't heard from them in a while. I mean, so where do I? Oh, we don't have these logos up anymore. University of Michigan is one of our board whatever members for academic institutions, and we're in their I can't remember what they're called, but their HPC center. And then, that's not HPC though, at least. Yeah. 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 And then there's a few medical foundations in like the East Coast and England, and I can't remember the names of the ones that I can say, but they do talks. If you search for Ceph in like a field you're interested in, you'll probably find something. CERN hosts Ceph days and computing days that talk about Ceph pretty frequent, like, every year or two, so you can find those archives and see sort of the HPC people talking about what they like and dislike about it. That's a change. Oh yeah, I mean, if you went from HPC to cloud and are coming back, Ceph is definitely the thing to look at. Yes. Okay. 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 So where an object is stored is not in a map. It's very important that it's not in a map. There's a map that describes the shape of the cluster, and then you use that map as an input to a calculation and say, if the object foo exists, where does it live? And then you go off and say like, okay, this OSD would be responsible for object foo, and tell me about object foo. And the OSD might say, I've never heard of object foo, or it might say, here's the object. But it's a calculation based off of the name of the thing you're trying to find and what the cluster looks like.
Okay, so how do you know where to write something?
The place that's responsible, that calculation spits out a set of OSDs, and you say, hey, first OSD in this list, I want to write this object. And, okay. Okay, so Ceph has its own custom system called BlueStore that speaks a Linux block device protocol out its backside. So it lives inside of a Linux block device somewhere that has a piece of software called BlueStore managing it.
Is it possible to lose, and what happens if you do?
To lose that, the disk can die. So that's why we have 3 copies, or 8 shards and 6 recovery shards, or with the erasure coding of the data.
The entire disk that we have to
Yeah.
synchronize that entire.
Oh well. Again, so it's always synchronized. When you do a write, it gets written down to all 3 places it's supposed to live before the write. Before you get the write back is done. So that's always done and saved. So there are people, you can run Ceph on all the Ceph daemons on a Linux host. A NAS would be a really small one. It has been done, and people do it for fun. I would not recommend it for anything meaningful, but it'll work. At least, if the NAS is actually a Linux system you can do this with. There are a lot of home lab users. If you go to the Reddits for home labs or Ceph, then you can see people talking about it there for on disparate. It's a lot more common to be on disparate pieces, but yeah. can get a long way. You can get a long way on an XFS RAID array, and it's going to cost a lot less.
I missed that part of the talk.
Okay. Yep. In the green, and then
Can a client that's mounting a SFS client mount it from different Ceph clusters at the same time? Or does it just have to talk to one cluster?
so a client can mount. I mean, it looks like a file system, so you can mount an arbitrary number of them, but there's no like. It's just different file systems.
I meant from the standpoint of it talking back to get its credentials from the cluster, like there's like the FSID information that client needs to know about.
Yeah. So a given client can.
Are you just targeting a different monitor services?
Yeah. If you're talking different file systems and different clusters, they're targeted at different monitors. Within the appropriate cluster. So they're just wholly independent from each other. But there's nothing that restricts that from working. Okay. Mm-hmm. So Ceph can run on commodity hardware and does, and you could install it on a Linux server that gives you Linux server access. And I have no idea what your, support expired hardware box looks like or can do technically. Yeah, so I mean, Ceph is not going to do anything that would prevent that, but I have no idea what hardware restrictions the boxes are enforcing on themselves. I have no idea if it's like a real Linux system. So I mean, Ceph definitely doesn't care. Ceph, like if you can boot the daemons on it, Ceph will do it. But yeah, and I mean there are many people who run Ceph on sort of expired or previously used systems. There was a talk at Cephlicon last year about the environmental joy of doing that because it was in the Netherlands, and one of the local supporters was like, the Netherlands has pretty strict climate reporting rules now, and so they were like, look how great this is for your legally mandated reporting systems. Yes, in the back. I don't think that's quite translating in my head. Sorry. Okay, literal UID translation you're asking about. Okay, sorry. Okay, Ceph does not, well, that's complicated. Mostly Ceph doesn't, but like there is the UID mapper is integrated in the kernel now, and you can set up Ceph so that a user can only act as a particular UID and do mapping inside of libcephfs, and the other layers don't really speak UIDs the same way, so mostly, but it very much depends on the details, because UID mapping is the whole thing. So much of it, but whether it works for your use case, I have no idea. Yeah, but I mean, like, that's the file system. Like block devices and UIDs or object stores and UIDs they're totally unrelated. So you know more about this than I do.
When you think about an RWO PVC that would be on a block device, for example, right? When you're gonna attach first the block device, then you're gonna mount the file system. So Cube is gonna lay the file system, and basically it's gonna use the well, the characteristics of the pod that is starting to lay down what user ID and GID you're going to use on that particular file system. So if someone was trying to remount that, if it doesn't have the same user ID, and I'm talking about RBD, but for CephFS would be the same, because for CephFS what we do is that we create a subvolume for that particular PVC. So your pod in your namespace are also going to use the UID and the GID that you use. So the subvolume will use that inside the file system that you lay on top of that directory, which is, but from a pod perspective, it looks like my file system. So then comes the problem, is that if you want to share a volume, and if you want to share between two pods that are inside the same namespace, well, you're good to go, right? You're in the same namespace, so you're going to use the same characteristics, unless you override in an actual pod. It becomes more complicated when you want to share that PVC across multiple namespaces. And then you come into tricky situations, and that's why a lot of sites, when they have to share an RWX PVC across multiple namespaces, what do they resort to? The good old NFS, right? Because it's easier, and I don't have to worry. So if you want to do it with natives, the native CephFS CSI driver, you would have to make sure that the two namespaces use the same security setting, FS group, UID, GID. So do you really want to do that? Then you get into those corner cases where it's acceptable when it comes to security, and other corner cases where security is going to say, no, you can't do that. So there are a lot of areas that we would have to discuss and inspect to figure out exactly what you want to do, but that's basically what's happening inside.
So we're now going to go to the live part of...
Yeah, I'm the one taking the risk. That's what he's not telling you.
But we didn't introduce JC. JC was the original trainer for Ink Tank. JC has literally trained more Ceph people than anybody else on the planet, including me. And he has pretty much won every recognition that Red Hat training is capable of giving somebody. So,
thank you. Well, yeah, I've been around quite some time, just for the fun. And it relates to what Greg was saying when he was talking about the different deployment tool that you have with Ceph, right? My first encounter with Ceph, and I remember the date, is actually February 2013. That was my first encounter with Ceph. And back then, the tool was MK-CephFS, right? And remember when Greg said that the original module, the reason of the Ceph project is the CephFS module, right? And that's why the tool was named MK-CephFS, right? Although the name of the project is Ceph, but the original module is CephFS. But anyway, so I've been around since February 2013. I've been doing Ceph. My first prototype was 2 months after that. Basically, we introduced that to a customer in Europe where I was working. Back then, I used to have my own company. I was a contractor. And then in November of that year, I became an Ink Tank employee. And since then, I've been doing Ceph almost every day. Ceph standalone, Ceph in Kubernetes environment with Rook, and I'm presenting next week at KubeCon in Paris. I've been doing Ceph on OpenStack in hyper-converged environments, non-hyper-converged environments. And I've been doing OpenShift with OpenShift Data Foundation and IBM Fusion, which is basically another renaming of it. So what I did is that we had to make a choice. We were limited in time. I was told 2 days ago that I would be here. So I come from Vegas. I'm not that far. So I basically created like 3 VMs on my laptop. And those VMs, for practical reasons, I did a training internal to IBM last week. So basically, I reused one of the VMs that I used for my internal training So it doesn't use the community Ceph version, it uses a downstream Ceph version. So that, and you will see the colors of the dashboard look very blue, right? So, but that's fine. It's the same code. So you have 3 nodes. I kept it quite simple. So scale node 1, scale node 2, scale node 3. Hopefully it's going to work. And what we're going to do is that we're going to build a tiny 3-node cluster. Each of the VMs basically has 3 disk devices, well, 4. 1 being the boot drive, 3 being drives that are empty that we will use as OSDs. Remember when we were discussing that one of the benefits of Ceph is that it's extremely flexible and designed originally to consume, like, you know, stuff that you have on the shelf or that you have left over, basically. To that extent, you can actually do it on a VM. It doesn't care. You know, as long as you have enough cores and enough RAM on your laptop, you can do it. You won't do performance benchmarking with it, but it will work just fine. So one of the things that we're going to do, and I copy-pasted some of the commands that I'm going to use so I can review them. The steps is that the first thing we're going to do is to do what we call bootstrap the cluster. So bootstrap the cluster is to basically start the minimal configuration we need so that we can bring up a UI and one monitor and one manager. And in that manager, we're going to activate one module called the Ceph ADM orchestrator module. And that, the responsibility of that module is to basically help us bring the Ceph cluster in an automated way and make your life easier. And I'm going to show you that compared to the old ways of doing 10 years ago, where everything was CLI based, you had no other way to do. I'll show you how we can bring that cluster together using the UI, so that for the people that want to get started, it's easy. For those of you who want, send me an email after, and we can just like share the email. I have a standalone version of that virtual machine that uses community Ceph with instructions on how you can get on your laptop, as long as it's an x86 laptop, you can bring up a single node Ceph cluster. So if you want to try the commands, how to query the API, test RBD, test FFS, test the Rails gateway, I'll share with you an OVA. You have to import that onto your laptop. So whatever VirtualBox works just fine. You can do with KVM, and then you follow the instructions, and you will do the basics, right? You won't do like crazy stuff, but it will teach you the basics on how to do it. Okay? So we're going to bootstrap the cluster. Then when we do the bootstrap of the cluster, what we do is that we generate an SSH key, a public key. So we're going to distribute that key to the other nodes that we have, so that basically my single mod and my single manager can actually start talking to these other nodes in the cluster. From there, we're going to assign labels, and you're going to see that basically the cluster comes to life. As we put the labels on the nodes, automatically the orchestrator module is going to deploy some new monitors, because we need 3 months at least in a production cluster. Then we're going to assign labels for the OSDs, and we'll deploy OSDs. So you will see that the orchestrator module, as soon as you say add some OSDs, is going to ask all the nodes, tell me about all the devices you have, and we'll do something simple, which is basically consume all the drives available on the nodes. We'll make it simple. Now you can do some more refined, things. Say only consume the SSDs, only consume HDDs. There are plenty of things that you can do, including consume only the spindles that are exactly 16 terabytes. Right? Or you can do when you create the OSD, put the data part of the OSD on a spindle, but put the metadata part of the OSD on a flash drive. So you can do all these refinements, and when I send you the instructions will be with that, and will teach you the format of how you can actually specify when you create what we call an OSD service, so that you can really refine what you want to do. And after that, we'll go in the UI, we'll deploy a Rails gateway, right? So we'll show you that you can create a Rails gateway, create an access we're going to do all these little steps one at a time, but we're going to start basically first with the bootstrap. Forgot to mention one important thing. What I have on that node is that I created a private registry using a Docker container. So Ceph does support being installed with the connection through the internet, so that you can pull container images, or you can do it completely disconnected, and you basically copy the container images in a private registry, and you can specify where is the actual container image that you want to pull when you deploy your cluster. So mine is going to be this one. That's my registry on node Ceph 01 on port 5000. Repo name is IBM Ceph, and that's the name of the image. That's the actual tag, bootstrap, the IP address of the monitor where we're going to bind so that we can become alive. So we need an IP address. And that's the one that I have here, 192.168.82.132. The registry URL, the password for the dashboard, and the username and the password to access the registry. Right? You can also override the location of any of the images that we're going to use to bootstrap the cluster. That's what I have in the override-images.conf. And when you get a copy of the OVA, guess what? You will see what the file looks like, and I can show you, do a cat on that file when the time comes. So what we're going to do first is that we're going to do a Ceph ADM bootstrap. So the bootstrap is going to create one monitor, create one manager. It's going to instantiate like the dashboard. Obviously, it's going to pull the container images. It's going to set the public network, the cluster network. I didn't specify specific. Remember when we had the questions about how many networks do you have? We have a public network, a cluster network. Then when you do S3, you obviously have the network where the S3 endpoint actually listens. That can be different from the Ceph public cluster and the Ceph cluster network. So you can have a whole bunch of networks in a Ceph environment. It's waiting for the manager to come out. It's activating the dashboard. It tells you where is actually the dashboard listening, which is Ceph 01 local domain. So what I did is that on my laptop, I just like modify etc host, right? So that I use like because it's a NATed IP address, because I use VMware Fusion, the NATed address is available like easily on the laptop, so I can actually go there without doing a port redirection. So I'll show you that. So this is done, and now what we're going to do is that we're going to do an SSH copy ID. So we're going to copy, set up. So we're going to copy the public key to one of the nodes, the Ceph 03. I'm going to copy to Ceph 02, just so that it's just like right here and available. And what I'm going to do, I'm going to list, I don't remember in what order I put them. And now we can go here, and if we refresh, we say visit. My old eyes are not that good. So by default, you choose what password that you want. So the default is I set admin and change me, obviously because it's the first time we get connected. Is asking you to change the password. Hopefully I don't make any mistake. Now I can reconnect. So this is our baby cluster. So it's a bootstrap cluster. So obviously it doesn't have much in it. It's just like it sits on its own. We only have one host. That's the node where we run the bootstrap. So we're going to see that we can add the nodes, right? So now what we're going to do is that we're going to add the nodes. So we're going to do a fun part, and we're going to do like an add using the CLI. We're going to do a mix of CLI and UI so that you can see. So what I'm doing is that I'm adding one node, right? So that's my Ceph 02 node, and I'm adding another node, which is going to be the Ceph 03 node, which is another IP address. And what I do is that I basically add, right, at the same time as I'm adding the node, right, I'm also telling the orchestrator module, well, that node is going to be a node to receive a monitor. That's what the dash dash labels mon mean, right? And if we go back to the UI, if everything went fine, we see that as it comes, we should start seeing the monitors, the number of monitors actually increasing, if I did it right. Here we are, right? So the first one, the first mon was the node that we used as a bootstrap, and because when I added the two other nodes, I gave them the label receive a monitor. Basically, the orchestrator module automatically, just like added, deployed a monitor on those two new nodes that I just added. You have nothing to do. You just add the node, say a mon should be deployed there, and boom, the orchestrator module just does it. Now we have two managers, right? One is active, one is standby. So remember when Greg said this, I don't know which one of the two said, no single point of failure. The whole concept around Ceph is that everything is scalable, and you have no single point of failure. So even manager, you deploy at least one, right? And at least one standby. So two managers always. When you do Rails gateways, yes, for a test, you can do only one Rails gateway, no problem. But what you would do is that you would deploy at least two, you would put a load balancer in front of it, and you would just load balance all the S3 requests toward the two Rails gateways. When you do MDSs, you deploy at least two MDSs, two metadata servers. One active, one standby by default. That's the default configuration, but then you can do two active and one standby, 20 active and one standby if you want. You choose, whatever, fits the goal. And we still have 0 OSDs, right? Now, the fun part is that by default, when you don't specify anything, it's just like, just want to see, why is the cluster, that's an interesting question. So let's see what it says. Oh, we have a clock skew. Damn, that's the part I forgot to do. Okay. So something, remember we said it's a distributed environment, so we need the clock. I didn't have that problem when I was home. Well, anyway. So everything we do is time-stamped, right? And because I forgot to configure basically cronny or NTP on those nodes, and Ceph is extremely sensitive to the amount of time difference between two nodes, and that's fine. It should, it should leave us alone for what we have to do. So now what we're going to do is that we're going to get in there. So we go into the cluster view, we go into the OSD views, and obviously we have 0 OSDs. And what we can do is say, okay, I want to make it quick. I want to consume, basically that's the default query, which is I want to do a cost capacity optimized based. The reason is it's a demo environment. I have only one type of device. It's all virtual drives. So you just do that. You keep everything. You see that at the bottom, if you want, you can select encryption. So you can do data at rest encryption. So when you deploy the OSDs, we're going to use LUX to create lockbox key partitions. And we're going to store the keys to open the lockbox in the monitors. So when the OSD start, if you do that, we'll use the key that is in the monitor to unlock the lockbox key so that we can read the key that will allow us to unlock the real data partition for the OSD. This way, if you lose the key inside the cluster, inside the monitor, well, basically, goodbye. You can't read the data, right? So we're just going to make it simple, and we're going to do, okay, just deploy OSDs. And if everything works, I'm the Bill Gates of or remember what I said, is consume all the drives available on all the nodes that are in the cluster. And right now we have 3 nodes, and each node has 3 empty drives. So if everything goes fine, 0 through 8, 9 OSDs, we're back in business. And we're going to see that the OSDs come up gradually, one at a time. And interesting enough, you see that on each OSD we have like a pair of statuses, one that says in, one that says up. In, the opposite of in is out, out, in, out. So in, the cluster will give data to the OSD. Out, the cluster will not give data to the OSD. What we give to the OSDs, remember the conversation around the PGs, replacement groups? That's what we give to an OSD. Picture the PG, the placement group, as like a floating layer above, so it's a logical layer that is floating above the physical devices. This way, when one physical device goes down, the PG that is in the middle, that is floating, we take it and we reassign it to somewhere else. That's the best way to see the placement group. That's why you don't really need to understand and go deep in the placement group, but that's really the usage. Up, the opposite is down. Up means that the OSD is responding and running. Down means that the daemon is either stopped or is like in a crazy clumsy place and is not answering to its peers because all the OSDs heartbeat each other. On top of that, to avoid network problems or some like corner case situations, the OSDs also heartbeat to the monitor. Right? Because imagine that an OSD would become completely isolated. Technically speaking, it's not going to be able to say, I'm not here. Right? So in that case, well, the good news, the mon is going to be able to say, well, that guy was supposed to heartbeat to me, but he didn't. And the OSDs also heartbeat each other so that when they protect the same PG, they can detect if one of the guys is actually up to date for the PG that is actually protected. And that's how we do the recovery and the rebalance, well, mainly the recovery, so that we can check on an OSD the version of the placement group that the OSD is actually protected. That's it, all the OSDs are up. So as you can see, we have like one PG right here. So this OSD has one PG, this guy has one, this guy has one, this guy has one. Okay? So that's the basic, and we have like a functional cluster, right? So we have monitors, we have managers, we have OSDs. If we have OSDs, we can store data. So one of the, because I have 3 nodes and I told the daemon to basically consume all the drives on all the nodes. And I have 3 empty drives on each node. So 3 times 3, 9. So what we're going to do, you can deploy a Rados gateway. So we're going to, gosh, my screen is so small. So I'm going to call it S3. I'm going to say deploy on month 01 and month 02. So you can also deploy by labels. Remember when we deployed the monitors, it was by label. Here I'm showing you that you can actually deploy a daemon, not by labels, but by selecting exactly the name of the host that you want. So it really depends what you want to do. So we're going to do 1, we're going to do 2, and we're going to do port 80, 80. We're not going to do SSL, it's a demo. So the reason I'm doing port 80, 80 is because on that VM that I use for my training, I pre-configured the AWS CLI to go to port 80, and to use a specific access key and secret key. So I'm going to show you also how you create an access key and a secret key on the Rados gateway. But basically, that's why I chose port 8080 and why I'm going to create one specific access key and secret key so that it matches the VM that I created. Okay? So we have the Rados gateway. I said deploy me 2 Rados gateways on Ceph 01 and Ceph 02, right? So here's what it did, running 2, size 2. So we're good. So we basically deploy 1 Rados gateway, 1 on Ceph 01, 1 on Ceph 02. I got my 2. Then I go into the object gateway. I'm going to create a user. So this dashboard user is the user that is used by the manager module that is the dashboard so that it can get statistics inside the Rados gateway. So that's the dashboard user that automatically gets created when you install. But we're going to create another one that is going to be just for us. Okay, email address. Tuk. And that's where it becomes out. I say, don't auto-generate the keys. I'm going to show you the keys. You're going to see they're super complicated. Very secure, right? No one, the first one that grasses, I'll go after you. Okay. So, no, I don't want to store that. So we created that, and I'm going to show you, I also prepare some set of instructions that we're going to demo and that we're going to use for the demo. So one of them is to list bucket, another one is to create a bucket, another one is to create a temp file, another one is to actually copy that file into the bucket that we created, list the bucket, get the data back, and then compare the data of where we are. So what we're going to do, I'm going to get all these instructions. I'm just going to do like, so I can recall them from here. So if I do an AWS S3LS, right, obviously it says no bucket, right? We created a user, but so far we haven't created a bucket. So what I'm going to do now is that I'm going to create a bucket. So I'm going to use the AWS CLI, the one that you can basically download from the AWS website that is available on many distros where you just say DNF or yum up your yum install, whatever, right? And we're going to create a bucket. And now if I list my bucket again, well, surprise, surprise, now I do have a bucket. Right?
What is the other step to make sure that AWS CLI is not using an actual AWS account manager?
Oh, it's like the standard AWS. So it's like so the way the AWS CLI works, so you can either pass a parameter on the command line, or you can use configuration file. That's what I'm using, or you can use environment variables. Right? Me, what I did, because it was easier, because I wanted to ship that stuff to my students, I basically created right, config and credentials. So config is where you define the endpoint. So in my case, Ceph01:8080, right? And credentials is access key 12345, secret key 67890. That's how I got it to work. So now what I'm going to do is that I'm going to create a temp file, which is that. I'm going to copy that temp file into the bucket. That's the one. Well, if I forget the, okay, so interesting to know, it looks like that command is slow, right, in the beginning. Well, there's one reason, is that the Rados gateway creates the pool that it uses. When you don't pre-create the pools, the Rados gateway will create the pools dynamically for you. So the first time, in my case, the pools didn't exist, so the Rados gateway created the Ceph pools. So the time to just like create the pool, assign the number of PGs, then the PGs get to peer between the OSDs, that's why it looks like it's kind of slow in the beginning. If you were to redo the command the second time, the CP would work faster because the pool's now already created. So how do we look at the pools? So, well, we can do that. So you can do from the CLI, that's all the pools we have in the cluster. And the last one we created to receive the data, that's that guy. The default.rdw.buckets.data, right? So that's the one. So we have like stored 10 megabytes. Remember the file I created was 10 meg? Surprise, surprise. roll space, 30 megabytes. Remember, we do 3 copies by default, so that's the 30 megabytes. And if you want, you can actually go back to, gosh, it looks so small. Right, so you can actually see that exactly the same from that end. Now, what is pretty cool is that we can do something funny. We can actually do that. We say edit. It doesn't want to let me do it. Damn it. So you can actually modify the number of copies that you do on a pool. There's one rule, is that you cannot change an erasure coding profile for a pool because you decide the number of data chunks and parity chunks. So obviously you cannot say, like, on the fly, change that. But when you use replicated on the fly, you can actually go from 2 copies to 3 copies, from 3 to 4, from 4 to 2, or from 4 to 3. And the cluster will dynamically remove the copies that you don't need if you went from 4 to 3, for example. Or if you go from 3 to 4 or 2 to 3, it will create additional copies automatically for all the objects that are actually stored in the pool. You just have nothing to do. You just let it, you just look at the thing just like doing the job while it's creating new copies. So that's, one of the things that you can do is like S3. We're going to show you also, just because of Greg, I made a few things here. I'm going to be the nasty guy. I'm taking risk, I'm telling you. So, what I'm doing here is that the first thing I'm going to do, if I'm using the wrong keys. So what I'm going to do here is that from the CLI, I'm going to tell, the orchestrator module to basically create one file system. Remember, he said that a file system is a volume. That's another name that you can give to a file system. So I'm going to tell the guy here, just like, please create me a volume, so a file system called Ceph. And as you can see, right, what did we do? That we are actually creating the volume. The MDSs are right here, right? We need MDSs if we want to be able to make a file system, because that's a prereq. We need an MDS to make a file system. So we're creating pools, right? And the pools are just like going to come up by themselves. And the cluster is now going to have a file system. Right? So we have one file system named CephFS. The metadata pool is called cephfs.meta, and the data pool is called cephfs.data. That's the pools that we have. Okay? Now we're going to do some more fun stuff. Is that we're going to take another risk, and we're going to tell the orchestrator module, please deploy me an NFS gateway on top of CephFS so that I can access my file system either using the CephFS native protocol or the NFS protocol. So I'm doing that, and what I'm doing after is that I'm going to do a little watch, because sometimes, I'm on VM, so the stuff is not like super fast. It's going to take a little bit of time to deploy the NFS gateway. So I just added to my instructions a watch that basically monitors the service that we create. I can see it just like get to 1/1, which means I ask for 1, and I'm going to see it coming. And once we have the NFS gateway running, then we're going to be able to do an NFS, a mount-TNFS, type NFS, right, so that we can actually mount the file system. And what we'll do is that we'll store something in a file using NFS, then we'll mount the file system using CephFS, and we'll add something to the file, to the very same file that we'll see. We'll have, like when we do a DF, we'll have one mount point that is with NFS and the other mount point to is CephFS. don't have that. So what Greg was saying is that CephFS, when you create a file system, is able to consume the entire space that you have on the OSDs. If you want to limit the size of someone, you use user quotas. And the quota will say, that guy, you can do more than that with the snapshot questions, obviously. Interesting enough, when you do Ceph in a containerized environment using the CSI driver, that's exactly what we use to, when you create the PVC and you say, I want a PVC 1 gig, right? What we do is that we actually assign a quota to the sub-volume. I say that sub-volume is 1 gigabyte. So when you reach 1 gig, game over. Okay, we're 1-1, so looks like we're in business. And now that the gateway is up, I'm going to ask to actually export the file system, the entire file system. I'm not making it complicated. After all, it's just a demo, right? To say, export the entire file system so I can access it through NFS. So that's one command. I know, again, NFS export right now, I don't think we can still do them in 6 because that's a version 6. In 6, we can do it from the UI. In 7.1, it will be in the UI, right? Which is like with the latest version that we have. So basically, I created an export called NFS demo of the file system called CephFS. And as you can see here, the path slash, I'm taking from the root of the file system. So my export let me actually see the entire file system, the entire CephFS file system, okay? And RW, read write, so that I can do something. Once I've created the export, I'm gonna create like a mount point, and I'm gonna mount that dude using NFS. Hopefully it works. That's usually, I told you, I'm the one that's taking the risk. These guys are just doing slides.
Hostname is easier or laptop?
No, hostname is the virtual machine, Ceph01. Looks like it doesn't like it. Unless something is wrong. There's no reason I would have forgotten something. It's not here, Ceph. Just like be careful. Yes, my stuff is running. It's actually weird. There's no reason it wouldn't work. It was working the last time. Okay, let's try something else. Let's see if we can. I'm going to create a mount point. I just want to see if I have the same problem. So it's just NFS that seems to, I don't know, unless I forgot something, but it doesn't look like it. So that's, remember we were saying the kernel module that you can use. So when I do a mount to Ceph, that's exactly what I'm using. I'm using the CephFS kernel module. So for the demo, I mount the entire file system. That's my mount point, and that's the file system that I want to mount, CephFS. So I mount slash in the file system called CephFS, and the username that I'm using is admin, because I just wanted to make it easier for me and make it work. Why is... It's not loaded, so it's not a firewall problem. No, it's just listening on the default ports for NFS, and it was working on a single VM, on my single VM. I haven't retried on the multi-VM. I'll check that another time. So basically, could be, let's see, where is, oh, it's running on 0.2. Okay, and that's the Y. I didn't check that. Okay, that's why the stuff I forgot, you see? Okay, so we're gonna do a touch, because we want to show that we can actually just like touch that file through NFS, right? Funny enough, if we do a DF, right, so we create like a dummy pool so that we can store NFS export information. And so that's our data pool for the Ceph file system, and that's the data pool for the actual file system. So in the metadata pool, right now we have 0, and in the data pool we have like 4 objects so far. That's what we have. Now what we can do is that I'm just too lazy to type the commands. It's been a long day. I'm going to store something in the file, right? So that's using NFS. So if I just like do that, this is my, and now what I can do is that, remember that if I look at my system, right, I have 2 mount points. It's the same thing that I'm mounting, one through NFS, one through CephFS, right? So what I'm going to do, the first thing, I added content through NFS using the NFS mount point. And now what I do is that I'm adding content to the very same file, but this time using the CephFS mount. And if I look at the content of the file, right, my first line is the first one that I added using the NFS mount, right? And the second one is the one that I added using the CephFS native client. You know, it's the same file. You know, one case access through NFS, the other time access through CephFS. So that's kind of the cool stuff that you can do. As Greg was saying, one of the great things, what I really like about the Ceph file system is that with the extended attributes, so you can actually have data that is in different pools. You could have like some directories that would be using NL-SAS devices, OSDs that use NL-SAS devices. It's more like kind of an archive workload. You don't care about the performance. But another directory would be using OSDs that have SSDs underneath because they need more performance. You can also, he's shy, he doesn't want to talk about all the cool stuff. We also do striping when we do CephFS. You can actually on the directory not only say I want these directory to live on that CephFS pool, right? That Ceph pool. You can also say I want to change the way I'm going to do striping. I'm going to use Rados object size that are different with a specific stripe unit and a specific stripe length. So depending on the workload, in some cases, you can actually adapt what you're going to do, not only the type of devices you use underneath, but also how you basically create and lay the data on top of the objects, the Rados objects that you create. It's extremely flexible. It's pretty cool. Another thing we can do, we can also show you, I'm trying to be on time, to do kind of everything. Block devices. So we can create a block device. So we're going to call it my image. We're going to do replicated pool. The autocorrect of that stuff is like crazy. PG auto scale off. I'm going to use the name RBD because I know up. Placement group, I'm going to do 32. I'm going to do replica 2. Applications, I'm going to say it's going to be RBD. Crush rules, I don't care. I'll use the default. I do not do compression. So I create a pool. So that's a pool that is going to receive some RBDs if everything goes fine. Did I create the pool? Wow, it looks like it doesn't want to refresh. Nope. So my pool RBD is at the bottom. It's empty so far. So then what I can do is that I can do images, and I'm going to create an image. I'm going to call it my image. I'm going to put it in pool RBD. size, I'm going to do, I don't know, 32, well, 1 gigabyte. I never remember how you spell that, no. I'm going to leave the default flags. Okay. Now if I list, that's the one, and I can do an RBD map. And I say my image. So the first parameter is the name of the pool. I'm cheating here, that's why I call the name of the pool RBD, because if the name of the pool is RBD, that's the name we use as the default pool name. So I put RBD slash to show you that the name of the pool could be anything different. Yeah. And RBD, so we now have one device, right, RBD 0, and what can you do? MKFS does xt3/dev/RBD0, and we can actually create a file system on top of an RBD. And then you can just like mkdir/mnt/myRBD, and you do a mount /dev/RBD0/mnt/myRBD. It's all thin provision, yes. Okay? And now I have my RBD, right? So I can do an ls/mnt/myRBD, and that's actually a file system that sits on top of an RBD. You use it like if it was like a regular file system on your Linux system. I've been asked to wrap up. That's because those guys took too much time. Okay, but that's all the cool stuff you do.